So I'm Matthew Vederick with Seabine Associates. I'm a senior consultant here, and with me helping present today, we've got Keely Seabine.
Hello, I'm Keely Seabine. So we're going to be talking today, we're going to go over just kind of an introduction to acoustics, give a kind of high-level overview. So we want to go ahead.
Yeah, 1 second. I'm going to hide the video here so you guys can focus on the screen.
Okay, perfect. All right. So this course has been made in collaboration with Seabine Acoustic, which is our acoustic consultant firm. We specialize in a number of different acoustic-related services that can be seen here. And with that, we'll kind of dive right in. This is obviously an approved CEU through the AIA. Our material is copyrighted. We appreciate you complying with that. So we're going to, as I mentioned, talk a little bit about acoustics. And, you know, acoustics can be kind of viewed as a term that might be kind of something that people aren't necessarily familiar with, or maybe they think that it only applies to theaters or concert halls, very specialized buildings. But we're going to look at a lot of metrics, principles, standards, and look at the way that acoustic consultants kind of get involved in projects, and just try to help everyone understand a little bit more about acoustics as a field. So at the end of this course, we should be able to have an understanding of the different acoustic standards, codes, and guidelines that exist. We're going to have an understanding of some basic acoustic concepts, and then also take a little bit deeper dive into some of the acoustic metrics that are commonly used in our field, as well as a few not so common metrics. And then the last portion will be the different ways that acoustic consultants are engaged in projects. And so with that, we're going to dive in. So why do we need to be concerned with acoustics? Well, we want to understand how acoustics relates to the health, safety, and welfare of all of the occupants of spaces, and not only that, but of the surrounding environment. Different acoustic environments are present in the different types of buildings, and they're each different building type and even adjacency type within buildings have their own acoustic needs. And so we're going to kind of look a little bit high level at some of these, but as you can see, some of the photos here, whether it's, you know, facilitating learning through the use of acoustic design, or to help promote healthy healing in healthcare design, promoting rest and repose in residential design, and protecting information, or creating a sense of awe and reverence in spaces of worship. All of these different building types incorporate different aspects of acoustic design. And one of the ways that we look at the health of our occupants in terms of acoustics is looking how sound may impact the kind of physiology of people. I'm sure most people are well aware that excessive noise can lead to hearing loss. But what you may not be aware of is that being exposed to sound at different levels can also increase a number of different physiological responses, whether it's increasing cortisol levels, increasing blood pressure and heart rate, and having bodies go into stress response. So therefore, there's higher risk of cardiovascular disease. And so there's a myriad of different physiological conditions that are associated with sound, and something that we need to kind of bring an awareness to as we're designing our spaces. We want to try to intelligently design our spaces so that we take all of this into consideration. When we think about the health effects of noise and and different populations, they tend to kind of fall into these two categories of the kind of healthy population for hearing, and the diseased population for hearing. And those are kind of separated by this threshold levels between 65 and 75 dBA, where sound levels below that level are kind of considered normally a healthy population. This might be someone who works in an office that may not be necessarily exposed to high sound levels all the time. However, there is a substantial amount of the population that is in fact exposed to high levels of sound on a day-to-day basis. And some of the sound levels may be above 85, 95, 100, and higher, depending on the type of industry that they're in and the type of work that they're doing, and the types of equipment that they are exposed to. And so understanding that there are different thresholds for different types of populations when it comes to hearing, and just understanding that it may be necessary to use hearing protection for some of these populations. When we look at safety, when we have spaces that are either too reverberant, too loud, too noisy, they can increase errors, they can increase any kinds of hearing loss, and all the physiological responses. And so really we want to look at safety as well when it comes to the acoustic design of many of our buildings. And so to protect our welfare, as I mentioned, all of these different types of spaces have a bit of a different need when it comes to acoustics and what we are trying to accomplish within these spaces, whether it's offices or industrial plants, performance spaces, or learning spaces. All of them have different areas where the welfare of the participants really needs to be taken into consideration. And in looking at that, there are now a number of agencies that actually provide acoustic design criteria and or guidelines or code requirements for the different building types. So first and foremost, we have listed on here the Facilities Guidelines Institute, FGI guidelines for hospitals. In Florida, this is now building code standard. So hospitals have a number of acoustic criteria that are contained throughout this guideline. And the criteria does seem to change a bit with each of the different iterations of FGI. So always going back and looking at what the latest criteria are for acoustics is important. For schools, interestingly, just this past year, the Florida Building Code has now incorporated the use of acoustic criteria in the building codes. So now there is actually a multitude of acoustic criteria that are contained in the Florida Building Code for school occupancies. This is also addressed with ANSI as 12.60, which was an acoustic standard written in the 90s. That has been very influential in a number of codes and guidelines and criteria. Multifamily and education, obviously the International Building Code and Florida Building Code have criteria for residential sounds for STC and IIC ratings. And the GSA also provides guidelines for federal office buildings, courthouses, etc., looking at STCs, RTs, and NCs. The United Facilities Code, the UFC, also addresses buildings on military bases. And so whether it's offices, schools, training facilities, and fitness centers, all of those have acoustic criteria. There is also a health code called the Council for the Model Aquatic Health Code that has acoustic criteria for the design of indoor aquatic facilities. So a number of different agencies have a number of different criteria for various building types, just something to be aware of and to know exists. We also have acoustic guidelines in WELL as well as LEED that are comprised of different sets of acoustic criteria for the different categories. We also have ASHRAE, which looks at sound levels from HVAC equipment as well. So, there's been this trend in the last 20 or so years that more and more agencies have developed more and more criteria, and I'm assuming the trend will continue. And so with that, I think we're going to jump into some acoustic concepts now, Matt.
Yeah. So we kind of looked over a little bit about, why acoustics are important in our buildings and how we can go ahead and incorporate them into intelligent design. And we're going to talk a bit more on that later too. But right now we're going to look at our second learning objective, and that is the acoustic concept. So these are kind of breaking down the kind of building blocks of acoustics, if you will. So just sound in general. Sound is a vibration that actually is traveling in waves. And so there's three basic terms that we're going to go over that are associated with sound here. And that's going to be amplitude, wavelength, and phase. So now, wavelength is related to the frequency. So this is what we hear as the pitch. The physical size of the wave, the wavelength itself, is going to relate to how many cycles per second we have, and that's going to be how many number of wavelengths every second will be our frequency that we measure in hertz. So if we have 10 cycles per second, we have 10 hertz. If we have 100 cycles per second, we have 100 hertz. So those wavelengths are getting smaller and smaller as we're getting to higher frequencies. Now, phase is the point of time in the wave cycle itself. So where we are within this, or if this shifts a little bit, there may be a phase shift as we move here. Another thing about frequency, so the typical human hears from about 20 hertz to 20,000 hertz. So this is from kind of low frequency to high frequency. You do start to lose some of that higher frequency sound as you age and have various hearing loss. Usually starts with that high frequency. So if you're a bit older, you may not still have the hearing up to 20,000 hertz, but in general, that's what we usually look at it for. We also mentioned amplitude. So amplitude is really kind of what we're seeing is the loudness, or is related to loudness at least, and that's going to be measured in decibels. So we'll go over a little bit more specifically about how decibels are logarithmic, but that is one thing that you're going to want to know and is key to this. How we look at and analyze sound. But right now we've just got a audio clip here that's going to play some typical sounds and their sound levels. It's not going to be the exact sound level based upon your speaker system or how your headphones or however you're listening to this, but it'll kind of give you a relative idea. So that's
Backyard insects, 50 dBA. Automobile interior at 30 miles per hour, 60 dBA. Restaurant noise, 70 dBA. Vacuum cleaner at operator position, 80 dBA. Lawnmower at operator position, 85 dBA.
So hopefully you were able to at least hear those on your end as well. But another thing we're kind of looking at here is with amplitude, we're looking at kind of both this positive and negative, this total size of the wave here between wave compression and wave rarefaction. You can see this here in the actual wave, the differences. And so when you kind of see sound waves pictured, obviously you don't normally see sound waves with your own eyes, but these pictures of them here, we can start to see that it has both that kind of peak and valley that we're looking at.
Backyard in
So, the other thing we kind of talked about a little bit was frequency. So again, frequency is, some may look at it as pitch as well, this kind of low and high frequency. And so, as we said, it's measured in hertz or cycles per second. So one cycle is the full kind of, both has the compression and rarefaction of this, so it's adds up to a larger part. And you can see here in this example, we have 2 full cycles in what we're showing is a 1 second time. So this would be a 2 hertz wave. Not something we can necessarily hear ourselves with our own ears, but just to kind of give you an example. And when we hear frequency, we think of either low frequency or high frequency a lot. So our ears are going to be more sensitive to middle and high frequency sounds than they are to low frequency sounds. But the middle and high frequency sounds are also where humans rely to understand speech sounds as well. That's where a lot more of our speech sounds are going to be, closer to those mid frequency sounds with a little bit in the high frequency. So we've got 2 little clips of tones. The 100 hertz tone here is probably going to be very hard to hear. But we'll see what we can get. So if you've got that. Now this 4000 hertz tone, I will give you a warning right now, it's going to be a high frequency. So just watch out for that in a second here. Yeah. So you can see there's a pretty big difference in those sounds, and we can see that's, 40 times here, that 40 times as many cycles in the same time that we're looking at. So the other thing, we talked about decibels being logarithmic. So there's different changes, and there's perception of sound as well. We don't always hear just a 1 decibel change. Some people, depending upon the exact frequency and their hearing, may be more able to hear that small change, but the typical kind of human hearer, kind of the typical human response, you're not going to hear most 1 decibel changes in sound. Now when we get to something kind of at 2 or 3 decibels, we're starting to just kind of hear that, see and can tell that difference a little bit. You get a little bit louder at that 5 to 6, you can definitely tell that it's noticeably louder when you're at 5 decibels here. And 10 decibels is actually heard by most people as twice as loud. But while it's heard as twice as loud, it's actually 10 times the sound power. So there's a bit of a difference there. We've got this next audio clip here is going to be different tones, or increasing in doubling of that. So it's a 10 dB difference from each tone that we're going to hear. So it should sound about twice as loud roughly. But it is actually 10 times the power with each step. So as you can see, each of those steps were definitely noticeably louder, and as you may even say again, twice as loud is what we'd be looking at that to be heard as relative to each other, but it is actually 10 times the power in each of those steps that we're seeing. So the other thing is, we talked about frequency as kind of individual frequencies or how it's broken up. But there's also kind of groups or ranges of frequencies that we tend to look at. And this is what we'll mostly look at in architectural acoustics. When we have something there, is you'll see a lot of things are either an octave band or 3rd octave band data when it comes to architectural acoustics. And so an octoband's a group of frequencies where the higher level is twice that of the lower level. Now, what are shown here in the table is just a quick example showing at the octoband center frequencies, and then each of those octave bands is then broken down into third octave bands. And again, so we start to see some of that. We typically have about 8 octave bands that are seen in architectural acoustics that are the main focus. Sometimes you may go a little above this or a little below this, but this is from 63 hertz to 8,000 hertz. And going a little bit higher in the high frequencies, but in the third octave bands, there are 25 from 63 hertz all the way up to 16,000 hertz. Now, 16,000 hertz is 1 octave band above 8,000, being that double that we talked about. And so we've actually got an audio clip here, a little bit of music that should be here to play. It's going to start with the broadband sound, which is going to be kind of all of these octaves, all the sound together that you're kind of used to hearing music as. And then it's going to slowly focus on each individual kind of group of sound. It's going to have some lower frequency, some mid frequency, and some high frequency. So you're going to hear the different elements. Almost like hearing different instruments sometimes that focus on it, but kind of focusing on that to see that what we tend to hear and what we have in music and life is built up of all these different frequencies. It's not just one. So we do have to look at everything. So this here, we've got that broadband music that we went ahead and were first talking about with you. So you can hear kind of those lows, you can hear those highs. It comes together like music. So here we're going to have some really low frequencies that you probably aren't even hearing for a second, and we're going to start to step up a little bit. You're starting to hear kind of those steps now, probably a little bit more to understand. Now we're getting to those higher frequencies as we get a little higher with each. And the very high frequencies. Now bring it all back together to hear it all as the broadband music. So yeah, as we said, decibels are logarithmic. Their sound is a form of energy, and so the loudness is measured in decibels, or dB. And so decibels are actually a dimensionless ratio. The equation here that we've got is just to kind of remind you that the metric for sound is, again, that logarithm. You can't just add sound levels together like you normally would other numbers. You actually, you have to have a reference level here for sound. In this case, we use sound pressure at the threshold of hearing is the typically used in architectural acoustics as that reference level. So to actually get a sound pressure level here, which is most typically what we're looking at, we see this as our actual specific event over that kind of threshold of hearing reference level. And then we'll get our decibels. So now, looking at adding decibels together, if you have two sounds, say 95 decibels plus 95 decibels, it doesn't add together to make 190. So the same thing kind of goes when we get into STC ratings. You can't add STC 50 and STC 50 and get STC 100. With decibels, it doesn't add that way either. So as we said, 10 decibel increase is 10 times the power. But when we have two sound levels that are the same, so we've got 95 plus 95, we actually get 98 decibels. We've got over here just a quick rule of thumb for adding together sound levels, and this again is a little bit more specific when you get into different frequency content and all, but general overall rule of thumb is going to be that if you're about the same level, maybe within a dB, you're going to add together 3 decibels on top of that sound or the louder sound. Now, if we've got two sound sources and the pressure difference between them is 5 decibels, then we're only going to add 1 dB to the higher level. So start to see that. And then if we're actually have our two sound sources and one is 10 dB or more, so we've got this example over here, 89 dBA or dB and 99 dB adding together, you're still only getting 99 dB. The 89 is not adding into it at that point anymore. So, which were, again, 10 times as loud for the sound power, or for the power of this, but we are, again, only heard as twice as loud.
Okay, so we've reviewed some acoustic concepts, and so now we're going to look at some acoustic metrics, which are basically just descriptors to look at different ways of understanding some of the acoustic properties in buildings. So we're going to start off with what we call the alpha bar, the sound absorption coefficient. This is basically a number that is on a scale from 0 to 1. 0, if a room has a 0 value in the alpha bar, that it means it's a completely reflective room. We either talk about rooms or even products having alpha bar characteristics. On the other side of that, 1 is a completely absorbent room. Now, for all intents and purposes, most rooms are going to have some kind of number that falls between 0 and 1. Most of them are going to be somewhere around 0.05 or so, up to, practically speaking, maybe 0.8 or so. That's kind of the range of rooms. And looking at this a little bit more in depth, we can kind of see where we actually want certain rooms to actually be very reverberant. Performing arts halls and theaters, we typically want an alpha bar in this space to be less than 0.1 because we want most of the surfaces to be very carefully sculpted and angled, but also reflective materials. So, that's kind of a special case. We come along here, and this alpha bar of 0.2 is what we would consider to be the break point between a live room and a dead room. So a live room is one that enhances the acoustics. A more dead room is one that begins to absorb the sound. So classrooms have typical alpha bars ranging from about 0.2 to 0.25 or so. Active social spaces, maybe if they are absorbent, which is ideal, would be 0.3 to 0.35. When we have spaces like hotel ballrooms, where most of the room surfaces are fairly absorbent, we might get an alpha bar of 0.35 to 0.45. And if we look at the next example, the tele/video conferencing room, ideally those rooms are very dead so that we're able to have a decent conferencing system and not have the acoustic finishes add a bunch of reflections into any type of conferencing or recording that's being done. And then at the furthest end of the spectrum is typically an alpha bar of 0.75 to 1 or so. These are the spaces that typically have the highest alpha bar approaching 1, where basically almost every single part of the room is covered in absorbent material, and it is very, very dead. This allows for recording to take place and does not allow for much room effect. Now, as a side note, there are different types of recording studios, and some recording studios like to, some artists like to have very, very dead, others like to have live, others like to have a mixture of live and dead. So those are very specialty spaces. Another concept, metric, excuse me, is the sound transmission class. Sound transmission class is basically asking how much sound does an assembly reduce when sound goes from one side of the assembly to the other. And this refers specifically to airborne sound. Airborne sound is the sound of our voices, the sound of people talking, of TV sets playing, these types of sounds. And so residential requirements have STC requirements for multifamily residential occupancies. Now, looking at this a little bit further, we can look at these three assemblies in front of us. The first, the two assemblies, STC 40 and STC 48 with a gypsum board and metal stud, one of them has an STC 40, one of them has an STC 48. What's going on here? Why is this happening? Well, if we look very closely, we see at the bottom here that the STC 40 has a metal stud that is 20 gauge, spaced 16 inches on center, whereas the STC 48 has a 25 gauge stud, spaced 24 inches on center. And so we have to be very careful when we look at the STC ratings, especially of gypsum board wall assemblies with metal studs, because the metal stud gauge and spacing make a big difference in the STC rating. Enough so that it may or may not pass building code depending on which is used. So just something to be very aware of. This is something that we see very commonly, having STC ratings that are not actually accurate because the metal gauge and stud spacing are vastly different from what's listed on a partition assembly. So looking at these next two, we've got the gypboard wall, STC 48, and the CMU wall, STC 48. Like, wait a second, why are those two walls, how do they have the same STC rating? If you're an architect, you know that those walls are a bit different. However, they have the same STC rating. What's going on here? Well, the STC rating only takes into account the kind of middle and higher frequencies and does not take into account the lower frequencies. So when you have something like a CMU wall that's very dense material, that's going to perform well in the low frequencies, and it's going to be a much better assembly if you are trying to block sounds, potentially music sounds or similar, that have a lot of low frequency components. So something to be aware of is that just because a wall has a listed STC rating, that does not necessarily paint the entire picture for how that wall performs. So it's just very important to keep that in mind. The more mass and the denser it is, typically the better it performs, but at lower frequencies. And so if we look at just a quick sketch like this is just to kind of show the STC rating of airborne sound. So if we've got people talking and having a good time in this indoor pool area, the sounds are going to go through the wall assemblies and travel to the adjacencies, sleeping and potentially teaching above. But there's also going to be these other paths that go through the floor slab or over the ceiling or through the ceilings, which we call flanking paths. And so this is just something that we really want to keep in mind, because when we're talking about trying to protect against airborne sound transmission, we're not only concerned with just what the walls are doing, we want to know what the entire assembly is doing, the walls, the floors, the ceilings, what the box around your space is doing, so that we can address all of those potential flanking paths intelligently. We also have IIC, which is Impact Insulation class. And so impact is the sounds of footfall, the sounds of stomping, the sounds of any kind of impact that you can think of. Chairs scraping the floor, kids dropping toys, the shutting of cabinets, any type of sound that basically produces an impact on the assembly, and then the sound is basically radiated through that assembly into the space below. We do have requirements for IIC ratings in the Florida Building Code for residential occupancies.
Yeah. So we talked earlier about what decibels are and how they're logarithmic, and you probably hear things measured in decibels. Another thing that we look at, especially in architectural acoustics, is what's called noise criterion, or NC curves, is pretty typical. So these were established for rating indoor noise from things like your air conditioning equipment or other building equipment. So it's another way that we can use to look at this. And you can start to see that these curves here, in the lower frequencies here, they're kind of much higher, and then it drops off down as you kind of get to these lower levels. So on the left-hand side, we have decibels, and you can see on the right, each of these curves is listed with an NC level. So that curve is kind of trying to help be more similar to what the human ear is going to replicate. It's not a perfect example of it, but it is a little bit closer to see that we don't hear the low frequency sounds as well. It's those mid and high frequency sounds that we mentioned earlier. We're going to start to go ahead and listen. So, but a lot of criteria out there is also put in NC levels for background sound levels of mechanical equipment in a building, or background sound levels of other noise within a building. So some of these, you may have something like a hotel room or a classroom at about NC 30, whereas if you're in a performance hall, you might be NC 15 to 20, or even less in some cases, but around there. And your gymnasiums are going to be, again, allow a little bit higher levels, closer to NC 45. If it's really large seating capacity and you've got a lot of speech amplification, that might move up a little bit closer to NC 50. But again, those NC 45, NC 50 spaces, those are loud background sound levels. You don't want to have that in, say, your classroom space, or you don't want to be trying to sleep in a space like that at your house or in a hotel. So it's just another way that acoustic consultants can use to look at the kind of how the sound is impacting people within a building. So one that many of you probably at least heard about before and maybe a little familiar with is reverberation time. And so reverberation time is the amount of time it takes sound to decay 60 decibels. So, and it's measured in seconds. So this is sometimes referred to as an RT60, but there's other kind of focuses on that. But anyway, this is, you may have a kind of typical kind of private office or a living room space is going to have that reverberation time around a half second, or like. But we may have a performance hall or other space, maybe a religious facility, house of worship, that has a little bit of a longer reverberation time is desired in that space. They don't want it to be so acoustically dead. So we might be looking at 1.2 or 1.5 seconds for something like that, even 2 seconds. You may even get it a little higher if they're doing something like Gregorian chants. If that's the focus of a space, they may want a very long reverberation time for that and for that specific sound. But then again, you have to watch out for that, because that may be good for Gregorian chants, but now your spoken word may be a little bit different, so you need it a little bit different or tune the room. So some of the things that have to be kind of kept an eye out for is reverberation is dependent on the room volume, the materiality, so whether these are reflective materials or absorbent materials, as well as then the shape and shaping of the room. So again, it's all kind of plays a role into what that reverberation time is. And there are even some things, such as some of the education spaces have criteria in reverberation time that are now required by the building code. If you join us again on Thursday during that presentation, we're going to go a little bit further about even some of those with education spaces and some of those requirements too. If any of you have kind of worked around an airport, maybe you'll probably be familiar, or at least heard about, an LDN, or an average day-night sound level. And so if you get contour maps from the airports, that's what they tend to go ahead and are marked in for all of those different levels. Now, an LDN is an average. It's an average over 24 hours, so a whole day. And nighttime levels between 10 p.m. and 7 a.m. are kind of penalized and given an extra 10 decibel weighting added to those nighttime levels. But other than that, it's just an average of the sound levels going throughout all of that different time. The thing with an average is, if you look at a graph like this, we see a lot of spikes. Say this is around an airport, you have a lot of different overflights possibly, and those planes taking off and landing. But those individual events are louder. You hear those planes louder, but you can actually have that average over the day can be quieter, so it averages out kind of those peaks in here. So just one of the things, say if you look at this specific example we have on here, it's showing an LDN of 50 dBA. Well, if we look at where 50 is, let me get a laser pointer here. On this graph, you can see that we have a lot of sound levels here that are above that 50. So all of these, some of these 20 decibels are heard as 4 times louder even than that. So if you have these individual events, these individual overflights, those can still be disturbing even if you design around that LDN. You're just designing around an average, not the specific things that may occur there. And again, so this is used sometimes from HUD for site noise, as well as the FAA looking at community noise metrics. They're going to really say anything above a 65, you really probably don't want to put residential there, especially without a lot of serious upgrades to those assemblies. And as you get higher and higher, again, that sounds, that 5 dB, 10 dB differences added on top of that aren't small, and it takes a lot more to reduce that. So the louder and louder your site is, the more impact and the more you have to do to enhance your building to reduce that sound from the inside. And there's not much we can really do on the exterior of that. So
Besides increased glazing.
yeah, well, if you're standing outside on the in walking into your building or have an outdoor area that you're trying to have, that LDN is going to be what you're going to hear at times, but you're also going to hear those individual spikes. So another common level that we're going to talk about is LAEQ, or an A-weighted equivalent sound level. So this is a single number value for a sound level. This is probably more typically what you're going to see with a lot of things. You may hear something be called a dBA, and as just a level is 60 dBA, 55 dBA. These types of things, they're not always using in LAEQ, but that A in there is the same here, and that weighting, similar to what we talked about in the NC curve, it's weighting again out of that low frequency sum, so it's going to be more what the human ear typically hears. So, but again, this is an average, and just like we talked about with the LDNs averaging over a day, an LAEQ has an impact based on how long you average that time value over. So you lose information kind of the more and more you average. Maybe you have a noise ordinance that says you can't exceed 60 dBA, but you go out and you measure for 3 minutes and your LAEQ says you've got a 57, so you're sitting there thinking, great, I meet. But then you actually go ahead and look through that and see that you're actually reaching sound levels much higher, maybe even 70 dBA during that. But because of that averaging time that you chose or that was chosen, it looks like you're meeting where you may not otherwise actually be. So you've got to kind of watch out for that. For, is it average over a second, a minute, 3 minutes, 10 minutes, like the LDN, a full day? So you really just have to keep an eye out for that, because it can get a little tricky if you don't know what you're actually specifically looking at. The other thing, so we talked about STC. OITC is similar, but it's for outside noises. So an OITC is an outside to inside transmission class. Again, this is focused on airborne sounds. The main difference kind of between this and STC is STC had more of those middle and high frequencies. The OITC, while it still has some of that, shifts a little bit towards the lower frequencies for sounds that are more typically associated with kind of the airplane noise, traffic noise, and even kind of mechanical system noise that you may have from these outside spaces. You know, you might have the neighboring buildings, kind of mechanical plants near the property line in some cases that you're getting sound from. Or you're near a highway and you need to kind of reduce noise from this. Or you're over by that airport again and you need to reduce these levels. OITC levels are typically going to be lower than the STC of the same assembly. So you just kind of have to watch out for that. But they're really focused on those exterior sound sources is what it's meant to kind of look at. And again, it's just a quick single number rating. It's not giving you the entire picture of what's happening in there. You can actually see the more detailed information from the tests in the octave band and third octave band data if there's something that really needs to be looked into. But if you just have the overall OITC, it's that single number rating, it kind of averaging out a little bit, if you will, similar to some of those others, as we're bringing data from a lot of frequencies down just to one number. So. And then DTC, your door transmission class. This one's not very as common, but is still sometimes need to be looked at. And it's going to be more of a field test that's going to happen to see how much sound's actually reduced by a door. And this isn't looking at the door and the wall and the whole area. You may do an STC test that has a door in a wall, or a field test that has an NIC. The test maybe is how a manufacturer may go ahead and test their door. If they have a sound rated door, they may say, well, as long as it meets this NIC rating in the field, that's what they'll kind of keep it to. But this DTC really focuses on just the area right by the door and what that door itself reduces, because doors and windows are typically going to be your weak points in an assembly. But you still need to have your doors to get into your rooms. Obviously, you can't just build a box out of all the wall that works great. You still want to be able to use your room. So that's why we might start to see things like sound lock vestibules for theaters or other spaces, or you may have doors where you're trying to keep things confidential, whether that's a conference room or if you're in government facilities like a SCIF facility and you're trying to keep things either secure or confidential. The doors actually can have an important role there. So, a lab test for a door is going to give you an STC. But, yeah.
So we're going to jump into now just the types of ways that acoustic consultants are integrated into everyday projects. We're going to try to go through this quickly, so bear with me. But there's two main ways. We consider them as diagnostics and design. So diagnostics are basically when acoustic consultants are engaged when there's some kind of problem with the facility. Maybe the sound in a space is too loud, too muddy, too reverberant. People can't understand each other. Maybe sound outside is just so loud that it's bothering all the neighbors. When there is some kind of problem in an existing environment, consultants are called out to do diagnostics. They come out and have different systems depending on what the problem is to take acoustic measurements and to run diagnostics so that they can determine potential mitigation solutions to actually fix the problem. But acoustic consultants are also many times nowadays involved in the design of buildings, working with architects and engineers, contractors and owners throughout all the design phases so that all of the acoustic concepts are addressed from the very beginning. So when we're just looking at schematic design, when we have napkin sketches on paper, and then as the design develops, looking at refining some of the acoustic concepts, and going into construction documents where looking at things like specifications for acoustic products and looking at reviews of all the details where all the junctures of two or more planes come together is very important. Also looking at CA services, whether it's coming out and doing site observations or measurements, and looking at post-occupancy to kind of ensure that the acoustic criteria are being met. One of the ways that we get involved in the design is the acoustic finishes. So there are many spaces that require very careful shaping and angling and very specific materials, such as the spaces that you see here, recording studios, theaters, concert halls, band spaces, music performance. But other spaces, typical spaces, classrooms, offices, airports, other spaces that may not need the kind of very detailed acoustic design of the finishes, but do need to incorporate them so that they aren't essentially a racquetball court. Another way that we get involved is through environmental design. So that's basically looking at how does our building impact the surrounding environment, and how does the surrounding environment impact our building. We look at environmental design, taking acoustic measurements on the site so that we can document what the existing sound levels are on the site, and by building noise maps, 3D noise maps, where we study what the sound sources are on our site, whether they are from our building or whether they are from the outside surrounding community, and propagate them across the facades of the building and propagate them, the sound levels, into the community so that we can study how our building and how our environment is impacting or will impact the built environment. We also look at sound isolation. So it's how the building assemblies, the facade, the wall assemblies, the floor ceiling assemblies, how all of these assemblies are built and detailed so that if we have to reduce sound from one side to the other, we're doing it effectively. We're looking at all of the flanking paths and we're taking into consideration all of the different adjacencies. We also look at mechanical noise and vibration control. This is where there are several different noise sources that are associated with mechanical equipment, and so we look at every single one of those sources so that we can determine how best to isolate, how best to reduce, and how best to make sure that the acoustic environment from the mechanical system is what it needs to be, especially in those spaces that require very quiet sound levels. Designing the AV system, audiovisual systems, is also a really important task. It's crucial that it's integrated with the acoustic finishes in the room, because you could go and you could spend, multi-millions of dollars on a new AV system, but if you have the speakers that are angled at the wrong angle, or if they are located in the wrong locations, you could have a room that sounds horrible, even though you spent a ton of money on that AV system. So AV system design is really crucial that it's integrated with the finishes and with the 3D modeling so that you can ensure that both of those systems work in concert with each other and help each other. So the question is, what kinds of buildings need acoustic design? Well, the answer is all. From airports and aviation facilities,
where you may be focused on the large groups of people walking through or the sounds of the planes outside, to civic and cultural facilities where you may want these special moments inside a museum or you have a courthouse or government building that needs a focus on those specific ideas. Education spaces, as we said, if you're joining us Thursday, you'll hear a little bit more about those, but classrooms, libraries, these large multi-purpose spaces all have very different acoustic criteria and acoustic needs. Whether you're in hospital and healthcare facilities, so as we talked about very early, how that can help promote healthy living and that actually help people improve better and faster. We have master planning communities, so you may have all of these projects or something like this, it's 3 city blocks. How does all of this interact with each other? How are we going to go ahead and not just what's inside one building by itself, but how does it impact the whole area and the soundscape of the area?
And looking at low-rise condos to luxury and high-rise condos and mixed-use buildings, all of these spaces require very detailed attention to acoustics to ensure that they provide the most robust acoustic environment possible. Hospitality as well, from resorts and hotels, conference centers to restaurants, retails, centers, cafeteria even. All of these spaces require acoustic design.
We've all been in that restaurant that's just too noisy that you don't want to eat there.
Yep, and it's a big topic in acoustics today is restaurant acoustics. Lots of corporate centers with their beautiful atriums, executive offices, and large open plan offices. There's a lot of acoustic issues that come with those spaces, and so making sure that they're looked at in design is so crucial to have a successful project.
And even your larger sporting events and arenas, you have these loud events that are happening on, but you also want to be able to hear clearly and understand what's going on if you're sitting in that very high seat versus if you're right down there on the floor. And even specialty buildings like this planetarium in Trinidad has very specific acoustic needs. But as you can see, all kind of types of buildings, many more than just what we listed, whether it's those museum spaces, a performance space, a recording studio, a theme park. All of these have a different environment that we're really going to look at, and that has an impact where acoustics can be crucial to the overall kind of outcome of the building. So thank you for joining us, and make your buildings sing.
Thank you so much. We'll take any questions. We've got a couple minutes, I think, for questions.
Yeah, I know Marilyn has been trying to answer questions while we've been presenting. She's also with our team. I think we forgot to introduce her at the very beginning, but I think she's been answering the questions as they come in.
Yeah, I think that you